Hey everybody. So Kendall wanted me to do this, so I'm gonna do it. That's what she said. All right. Predicting products for a single replacement by using the activity series. So you have this chart. This will be given to you, and you can use it to determine what's going to happen when you mix a metal with a solution of some other metal. So up here, you'll notice we have the usual suspects of things that love to lose electrons and become ions. So sodium likes to become sodium plus one, and calcium, calcium plus two. These are things that want to happen. They're not very electronegative elements. They prefer to lose electrons pretty quickly to become, that should be plus one. They prefer to become ions and get into compounds. Whereas down here at the bottom, these have a high electronegativity, especially for metals, and therefore don't like to lose electrons. They like to keep their electrons, so they stay as a metal that you would see in jewelry or in wire or whatever. So that's why we're seeing here that we have silver, we have platinum, we have gold, we have copper. Mercury is widely used as a metal before we determined it was toxic. So these down here are metals that won't react, won't get into compounds as frequently, and they stay neutral or uncharged. So what does that mean for you? That means that if I give you a reaction like calcium fluoride, you'll see here the metal in the ion in the compound is calcium. And the question is, would that switch places with zinc? Would zinc kick that calcium out? But since these react up high and they don't react down low, zinc would prefer not to react and just have calcium stay in that. So this is no reaction. And the way I've been telling you in class is that up the higher up, these like friends, all right? They like to be coupled with something. They like to be in compounds. And down here, they like to be alone. So that is the situation there. Now let's do another one. So silver nitrate with magnesium. So silver is here. It is currently with a friend. It is currently in a compound, and magnesium is up here, and it is currently by itself. Up here likes to have friends. So compared to silver, magnesium is definitely the one who would prefer to have the nitrate. So we would make that plus silver. Now I'm saying NO3 too because magnesium, you may recall, has a +2 charge. So it would need two -1 nitrates in order for that to be balanced. I'm not going to go crazy for that right now, as long as you're understanding the basis of what we're talking about here, that silver would be by itself and would come out a solution. And in fact, we did this reaction, no, we did it with copper, but a very similar reaction in the lab that we did. All right, so notice that aluminum with acid. If you've ever used aluminum foil and acidic food, you may notice that it starts to corrode and whatnot like this. And that's because, actually, let's just go here. Here's aluminum. Where's aluminum? There it is. And here is hydrogen. So hydrogen being in an acid. So if we had aluminum, which is what aluminum foil is made out of, and some acid like HCl, which is a little strong for food, the hydrogen would prefer not to be in a compound in the presence of aluminum. So the hydrogen would come free and the aluminum would go in with the chloride. And again, aluminum's +3 and chloride's -1. I'm not going to crush you on that. All right, so let's look at some more. Here's tin, SN, and aluminum chloride, AlCl3. So aluminum's here. Let's change the color just so you know I'm talking about something different. So here's aluminum for that one. And here is tin. Where's tin? There's tin. And there's tin. So of those two, tin would want to be by itself. Tin is by itself, so this would do no reaction. Everything is where it wants to be. Aluminum is happy to be in a grouping with the friends, and tin is happy to be by itself. So this next one is magnesium. We'll make that green. Magnesium plus HCl. So magnesium is somewhere up high. There it is. Magnesium's there, and HCl is again hydrogen. So hydrogen would prefer to be by itself in the presence of magnesium. So therefore, that would go to magnesium chloride plus H2 gas. All right. So hopefully that makes some sense. So this activity series is what you use when we have single replacement reactions, reactions where something's by itself, and things stop working. There you go. Gonna sing you some. There it comes. Cold water. All right, so we won't deal with that. But anyway, dissolving of ionic compounds. We talked about this. Ooh, look at that. Let's watch it. Let's watch this, kids. Here is how I'm gonna turn them down a little. I don't know if you can hear this, but basically, sodium and chlorine get pulled apart by water. We've seen this a few times now. So the hydrogen ends, the positive hydrogen of water are going to pull out that Cl minus. That's the Cl minus leaving. Where's my thing? That's a Cl minus. This is an Na plus, and the negative oxygens will surround that Na plus and be pulled away. All right, that's weird because he's just talking in my head. Can't get to the next. There we go. All right. So before the reaction in a double replacement, you would have something like sodium chloride and silver nitrate. And then the silvers would find the chlorides, right? Like that. And they would precipitate in the bottom. And then all that would be left is the sodium and the nitrate floating around. And that is when a double replacement shows a reaction. So if it forms a solid, then things are happening. Solid. All right. If before the reaction you have something like potassium hydroxide and sodium chloride, and then after the reaction, nobody found each other, nobody wanted to be a solid, nobody wanted to make us, so everything here is still aqueous, then we say this is no reaction because basically it's just things dissolved in water before and things dissolved in water after. So nothing exciting happened. The way you figure this out is with this chart. So this is the double displacement chart. So you're going to switch out your metals. So in this case, the calcium is going to go with the sulfate, and the potassium is going to go with the nitrate. And then you're going to go to this chart, and you see here's the potassium, and here's the nitrate, and that is aqueous. And here's the calcium somewhere there's the calcium, and there's the sulfate. Is that what it was? Yeah. And here's the sulfate. So those two are insoluble. So when these react, this will become a solid and this will stay aqueous. And this is the reason there's a reaction, because that solid is formed. So copper nitrate with iron sulfate, you're going to switch out your metals. So the copper will now be with the sulfate and the iron will be with the nitrate. And then you would come to this thing again and you would look for copper, which is here, and sulfate, which is there. So copper sulfate is aqueous. And then what was the other one? Iron nitrate. And iron, either, let's go with, say it was 2, and nitrate is here. So aqueous. So iron 2 would also be aqueous. So there you have it. So this would be no reaction because both of these are aqueous. So this one's no reaction. So you will always have these charts on anything you would need to do, and you would need to leave those things. So let's try that one, I guess. So the sodium is going to replace the barium. So it would be sodium nitrate plus barium sulfate. And then you go back to your chart and you see, let me change the color of my pen because we're on a new page here. So this barium is here and the sulfate is here. So barium sulfate is insoluble. So that's going to make something happen. And the sodium was with, what was it, nitrate? Yeah, soluble. Sodium and nitrate are soluble. So this would be aqueous, but this would be a solid. And that would be the reason the reaction goes. For potassium acetate and silver nitrate, you're going to switch out your potassium